Hi everyone. I hope I can assume like there's already assigned a group of people who are taking the note for this lecture. May I know who are you? We have four people. Yeah. In between the talk, if you feel I go too quick, just let me know. Feel free to stop. Yeah, just let me know. Okay, we can start freely. This topic, actually, spin of the coupling, is something like actually first it's really just related with many textbook knowledge, and but here since my second lecture on Thursday will be topological insulators, and then I will make this concept as close as possible with the topological system, and then okay. Here, I will mainly talk about two directions. One is like similar coupling in the atom. This is a typical textbook. And then second, we will see in the solids or in a lattice and how spin of the coupling behave. How will it change the band structure and induce you a new effect. And for example, like the rush bar, dress house, and also some new effects like the graphene people didn't recognize before. And here from this cartoon, you already see something like this is just one electron is going around a nuclear, like the hydrogen-like atom, and this is an electron moving in the lattice. But here, what I will repeat many times in this talk is, here, the main important physics is the relativity. Relativity simply means here, we centered at this nuclear, the electron circling around. If we look at the electron, this nuclear also circling it around. And just we change the thinking or we change the coordinate in this way, we will get quickly the idea of spin of the coupling. And this is same in the lattice. Like in the lattice, one electron moving around this nuclear lattice. And if we focus on the electron, we let the lattice move, then we will get a different effect. And this is closely related with spin of the coupling and other related relativity effects. And this is a hydrogen-like atom. Let's just start slowly from the textbook. We know a hydrogen-like atom. This is a nuclear, this is electron, and the electron is circling around in this electric field generated by the nucleus. And here we know this is the potential, the Coulomb potential, the most simple one, is inverse to R. And then solve the Schrodinger equation, and we will get the energy level. This is the energy level. It's like this is the N, is the quantum number here. This is the orbital number. And then we also get the orbital. We know this is the first S orbital. Actually, most important information is inverse to Z. Z is the nuclear charge of this hydrogen-like electron. And here, this is the velocity for the 1s orbital is proportional to Z. That means you have more charge, then it moves faster. If you have more charge, the radius is smaller. And then let's get a roughly feeling. Oh, not yet. And then simply to derive this velocity, we can just use this classical information. This is the kinetic energy. This is the potential. And in this way, and we simply get the velocity is proportional to Z. And if you have any questions, just feel free to ask. And then here, what is this? This is the electric field. This is just say the electric field filled by the electron. And here is the gradients of this potential. Then we get this is I squared inverse. This is just the Coulomb attraction formula. And very important is here it's proportional to Z cubic. And Z cubic means here we have 1Z, but here R, this R is inverse to Z. Then we get this cubic term here. And here, from this hydrogen-like atom, we simply get one idea, like if this nuclear charge is larger, then the electron move much faster in the core level. And here in the 1s orbital, this nuclear, this atomic radius is much smaller. And here, this electric field should be much, much stronger. This is not some surprising conclusion. And then, however, if we go a little further, let's get the number, roughly a number. We know the hydrogen, this 1s orbital, 1s state, its energy is 13.6, the textbook value. And the Z is still the nuclear number. We get the radius. This is the Bohr radius, like a half angstrom of hydrogen atom. And then here, how then we look at the velocity? We calculate from this number. Actually, this is Z. It's like it's 100th of the light velocity. Here, this is the key point. We realize actually the electron inside the atom moves quite fast. How fast it can be? Suppose Z, in the periodic, Z is the element number. If the hydrogen is 1, just 100th of a light speed, okay, not very different. There's not much strong relativistic effect. However, if Z, like for example, is 50, then we arrive half of the light speed. Then for sure, in this case, the relativistic effect will be super strong. And here we know this is the Lorentz factor. And this Lorentz factor tell us how strong the relativistic effect will be. And we remember in the textbook, or even in the public book, we know that if the particle, the speed of the particle is super fast, close to the light, then its mass will increase, right? And this is proportional to this Lorentz number. And then at that time, we also know the distance will be shorter in that case. And then that means here, exactly, here this is the radius of this nuclear. This radius will be inverse to the mass. Then radius will be much smaller. That means then we can imagine for a small hydrogen atom, okay, it's just move relatively slow, just 100th of the light speed. However, if you increase the element number like to 50 and to even larger, we have many large heavy atoms. For example, to mercury. Mercury will be 64 around that. And we will get half of the light speed. In that case, this gamma value will be not that negligible. Then we will see the electron inside the core. Here I just talk the 1s orbital. Inside the core, its mass will be much larger than electron mass, usually like for example 20% larger. Then its radius will be much smaller. And this change will make dramatic change in the electronic property. Then let's see first what will change. And this is okay. This is I said. Let's change the coordinate system. And if we look at the electron, then we know there's a nuclear circling around. And we know first this electron will feel the electric field of this nuclear. And then the second, what you will feel, actually this electron will feel an additional magnetic field. But what's the magnetic from? And here I just copy that figure here. This is the electron. And this is the nuclear. Let's see, the nuclear move in this speed. Speed v. And, for example, then the electric field for the electron will feel, this is the electric field E. Here, in this coordinate system, here the electron just moving with the speed, circling around. If we change the system, when it moves quite fast, here we have to go to this Lorentz transformation from one coordinate system to another moving coordinate system. And this is the Lorentz transformation for the relativity. And, well, don't be afraid. Here we will only care about this term. Others doesn't matter, really doesn't matter. This is B, just the external magnetic field. In this atom case, we don't have that field. Then we only have this gamma and V cross E term. And V just the velocity, is the velocity of the coordinate system. E is the electric field. What we already had, we have just E and V. this E and V will generate simply a magnetic field. This field, like, is this direction. And, well, I think this one, here, this formula, well, maybe you already forget it, but don't be feel shame. I also copied it from Wikipedia. And this, yeah, there's nothing more, just we change the system. And this is a new coordinate system. This system has give you a velocity. Then we get additional magnetic field. We simply see in one coordinate system we don't have magnetic field, but when it's moving, it generates an effective magnetic field. This magnetic field will just act on the electron. But how the electron feel the magnetic field? Anyone has an idea? Yeah, not that complicated actually. Just because electron has a spin. Yeah, spin. Yeah, if you have a magnetic field somewhere, then you put a spin here. This spin just prefer to align together with the magnetic field. That's all. Then here just two information. One information is this moving electric field generates a magnetic field. Second, you have the electron has a spin feel the field. And as long as it's a field, we know usually we write the Hamiltonian in this way. This is the spin moment. This is the external magnetic field. This Hamiltonian simply tell you they prefer to pair level. If spin is anti-pair level, its energy will be a little higher, and like your energy level will be split. And okay, here we go a little more how to derive this formula and why it's called spin orbital coupling, not spin electric coupling, right? And here, actually we know here the electric field can be written this way. Here this psi is the potential, just the Coulomb potential. And we rewrite B in this way. And then actually we know that R cross P is the momentum, is the angular momentum here. The angular momentum of the electron. And then we derive the formula in this way. Just here mu dot B. This is the electron field, the magnetic field. And then we put B and mu here together. Then we get S dot L term. S is the electron spin. L is the electron angular momentum. Actually, it's related with the velocity. And that's why here it's called spin orbital coupling. This orbital simply like, let's replot it maybe in the classical way. This orbital, like we know, this L can be 1, 2, 3, and this we know we also call their SPD orbitals. And this just that. Is clear here? Yeah. Good. By the way, this formula, actually here, like here, when we derive here, like I didn't put gamma here. If one derive it fully from the relativity, and one will get some 1/2. Can you see it? Can you read the 1/2 here? Yeah, just a factor, but it doesn't matter too much here. Later then, here, I just repeat again here, from the relativity, we get the magnetic field. Well, in an electron, before we thought there's only electric field around, but actually the moving electron will feel an effective magnetic field. This field acts on the spin. And then this will change the energy of the electron. And this is the Hamiltonian of the relativistic effect Hamiltonian. And it's, here you will see, this is the spin of the coupling term, and here this is the energy, the gradients, the last term. And don't be scared about this. And this is just here, this is the electric field, this is the momentum, this is the spin. This is purely spin of the coupling term. And however, there could be a little more is, let's say here. there are several terms. This is the kinetic term. This is the term including everything. A is the effect of external field. If there's no external field, just forget it. And then this is the potential. This is the spin of the coupling term. What's that? Sorry, I told you. What's that? This. This is external magnetic field. Forget it. Doesn't matter. And this is the mass correction. This is the I said. When at the very beginning I said, if the velocity is very high, we will see the mass will increase. And however, when we derive this part, we didn't mention that. Then this is still later related with the mass correction, and this is called Darwin term. Actually, it's related with the velocity correction. And actually, this Darwin, anyone know who is this Darwin? Well, he's the son of the Darwin. Yeah. And then actually, all these last three terms, they are closely related with the relativistic effect. And in the early literature, actually, is here anyone who is doing band structure calculation? Oh yeah, good. I think in the early literature, like especially about the pseudopotential method, like for example, before 1990, at that time, actually this term was not included in the pseudopotential. There usually in the literature you see for some heavy element you see very different band structure, and after a point all these terms are included in the pseudopotential. Now roughly they are correct, and then actually this part will be also quite important, and as I mentioned, and although only here called Smelter coupling, but here this term they actually just from the same source. If you are electron, you're moving super fast in an atom or in the lattice. Actually, you don't care which term is which. You just feel a very effective, very strong relativistic effect. The mass is the mass is larger, and you will see a shorter distance, and you will feel an effective magnetic field. And here, only give you a rough feeling about the energy scale. Here we know this is not a good idea, use this unity. But here, we know roughly the kinetic energy is in the order of, yeah, please. Are there or not? Oh, no, it's not perturbation. Yeah, just main just dynamic. Yeah. Oh, sorry, I just copy a figure. And the kinetic energy is in the order like of 10 eV or 20 eV, even more. Like for the hydrogen, it's 13.6. And this is external magnetic field. This is Zeeman field. And here, this correction, like spin orbital coupling, this number is around like maybe around 0.1 to 1 eV in that order, smaller than 1 eV. And these values are even smaller. But this will be quite depends on the system. And for example, we know these values, they are really scaled by the element number Z. And here, as we repeated. And here, I will see again, here, we see this effective magnetic field is proportional to Z4. And why is Z4? It comes from here, actually. We know R, where it is. Yeah, R is inverse to Z. And that's not E. Where is E? E is Z cubic. We know, get it, right? E is Z cubic, and V is linear to V. Then we get the Z4 here. And this Z4 clearly tell you if you increase the element number, you quickly increase this effect. And maybe in hydrogen, in silicon, you don't see it. But immediately, like from silicon to germanium, even lower, what is below germanium, is tin. Tin and lead. And quickly, you will see a lot of difference in the electronic property and even in the material. Like in many material, you will see even their color are different. Okay, this is the one consequence. Let's see. Since we mentioned the energy scale of them, like will be in the order of like from milli eV to 1 eV. This is one example of the sodium light. And I think everyone knew it. And before people say, like, we know there's a light emission hopping from the p orbital to the s orbital. And this give you the yellow light. However, later people observe this light actually in spectra, they split into two spectra, like there are two. Their wavelengths are different. And what caused the reason? Actually, when people first discovered this effect, people first think about maybe electron has a spin. Then electron has a spin. Then this is the spin feel some effective magnetic field. Then since you already know the splitting, you can easily estimate the magnetic field. However, you get magnetic field like it's 18 Tesla or 20 Tesla. Anyone do experiment here? Like magnetic field? Oh, great. Yeah, I think you know easily what 18 Tesla means. Like in the normal lab, what you ordinarily realize is 9 Tesla, your device, your PPMS. And you improve it, maybe go to 14 or 15, but here is almost impossible. And to like go beyond 30 or 60, you have to go to really many high field labs. And however, this means like in a sodium atom, just simply an atom inside sodium actually is very light, just a little heavier than hydrogen. And there is some like 20 Tesla magnetic field. This actually, yeah, at least at that time is quite unbelievable. Then people start to think, yeah, why? It looks there is very hard to find the other explanation, but why? Where is this magnetic field from? Exactly, it's indeed from the spinor coupling. And anyone knew the history about who first got the idea? This is related with spinor coupling. Oh, yeah, indeed, actually, it was Einstein. Einstein first think about. Hi, Andrew. First start to think about the relativity effect. And here, indeed, yeah, as we discussed here, this E cross B term. And from the simple calculation, one can really get the number of that for sodium. And this is one experiment consequence. As we will see, there will be a lot of more. For example, one is called SP contraction. And as anyone know what does it mean, or any chemistry student here? No? Okay, maybe I should talk it later slowly. Here, this is just a number. For example, I put a number for mercury, and this is the velocity. If we usually we estimate the velocity of this 1s electron. Well, mercury has many electrons, many shells. Now we only talk about the 1s, the most inside electron there. And its velocity, and here, if we count it in the atomic unit, and it's usually scaled by the element number. For example, mercury is 80. And here, 80 is the speed, and the light speed in this way is the Hyperfine constant, is 137. And then easily, we get this Lorentz factor is 123%, and it's increased a lot. Here, you will see the mass increase 20%. And then the radius decreased to its 80. And then what's the consequence over here? And important is, it will tell you something. First, the radius decrease tell you something. If inside the s and p orbital, they are moved super fast, and their radius are shrinked. Then after the shrinking, they screen the nuclear charge a lot. Then the outside, the D shell, will feel much less electric field. Then the D shell will increase in the radius. And this increase, it's a little complicated. Let's see. First, we have the SP shell inside. We have some D shell inside. Then further, we have some additional S shell outside. And this is here. For mercury, what is core electron? It's D10, S2, O5, D, 6S. And here, actually, here, let's see. This part shrinked a lot. The atomic radius shrinked a lot. Then screen the charge, then this d orbital will expand. After the expansion, actually, it's less screen this part. This make this orbital shrink further. Well, there are just 3 steps, like let's see. This one shrink first because it moves fast. Because it's shrinking, this d will expand. After the expansion, well, the shrinking comes to effect. First, the radius is smaller. Second, its energy will be lower. It gets more and more stabilized and just strongly attracted by the core. Then the consequence is this d orbital will just expand a lot. And because it feels less charge from the nuclear. After the expansion, its energy will increase. And then after its expansion, this most outside S electron will see more charge from the nuclear. Then this part will shrink. Why we care this one? Actually, usually this valence shell, they are most important for the electronic property and chemistry. All right? Then now we get a point. Because mercury is too heavy, then we get it's like 6s orbital. Its energy is lower. Like its radius is also lower. It has a smaller radius than it was thought without this relativistic effect. And then one consequence is like we get mercury. Why mercury maybe is the only room temperature liquid metal among all metals, right? One reason, actually one explanation is like because its core electron, these valence electrons, its radius just much smaller. Then if you put 2 big atoms together, there's not enough valence electron to form the chemical bonding. This bonding is much weaker. And then the consequence is like between two mercury atoms, the electron between them is mainly van der Waals interaction. They are quite weak. Therefore, mercury, they don't form a lattice at a room temperature, but they just become liquid. And this is one, and, okay. As we said here, this 6s, its energy is much lower. How low it is. And how low it can be. It will be lower like by in the order of EV actually, not just like 10 millieV lower. Let's see here, I will mention this material, mercury telluride. Let's see. And maybe it's better we compare with its partner cadmium telluride. Where is cadmium? Cadmium is here, just one column above the mercury there. All right. Then it has the same valence electron, however, just it's much lighter. Cadmium telluride, we know when we form a material, like we know cadmium has 2s electron, has some s orbital, TE energy. This is cadmium S. This is tellurium P and S. This is the atomic orbital. When they form a material, they will hybridize together, right? But for this one, there will be no surprise because this is a metal. This element will just take all the electron to it. Then when it forms a compound, this is the s orbital, this is the p orbital, this is the s. But tellurium S, tellurium P, cadmium S. This is the energy gap. It's an insulator. This material is a simple insulator. And actually, this applies to most of the semiconductors, for example, gallium arsenide, and even silicon. Let's see. There's empty orbital at the valence band, at the conduction band, and this sp band, they are filled as the valence states. What will happen for mercury? As I said, suppose this is the beginning, selenium P, S, mercury S. Just because of this S orbital contraction here, this S, its energy will be much lower. Actually, its energy will reach here. And then we have P orbital here, S orbital here. Actually, the firm energy will cross this P orbital because P has 3 orbitals. We have Px, Py, Pz here. And force the degeneracy. Then the consequence is, here mercury telluride is a semi-metal, or it's a metal. There's no band gap. And the cadmium telluride is a typical semiconductor. And actually this material was used for solar cell. It's a famous solar cell material. And here, just a zero gap, or whatever you call it. Zero gap semi-metal semiconductor. And then the main difference is just mercury is much heavier. And it's closely related with this contraction of these sp orbitals. Actually, this is happened from the inner shell, from the inside S, and then it get outside, affect the d orbital, finally affect the most outside S and p orbitals. And this is also, later I will mention, this is also one reason why mercury telluride was discovered as the first topological insulator. And it's mainly because of such special band structure, the relativistic effect. But I will talk about the details tomorrow. Is tomorrow Thursday? What time? Tomorrow is Wednesday. Yeah, then it's Thursday. And then the second example. Oh, yeah. Sorry. First, you understand the S is lower than P, right? Yeah. And here, I repeat. First, totally, we have just 8 valence electrons. And here is 2, there are 6 here. Totally 8. Then you have S and P, you fill all the 8 electrons. Then you get a gap here. Here is a band gap. If you have a band structure like this, P is like, I didn't see, P is XYZ. And you fill 2 electrons here, 2 electrons here, you have only 4 here. But you have 6 orbitals here. Yeah. Then these 6 orbitals, they're degenerate. And then your firm energy can only be here. Just cross some degenerate p bands. Yeah. Okay, the second example is gold. Let's see. We know the color of gold. Like gold is here, close to mercury, just a one number smaller than gold. And let's see. We remember like the silver or aluminum or normal metal. Metal just metal color, right? And what is metal color? Can we just like a silver and this white color. And like also aluminum. And this is color. We know color just from the reflection of the light. And we know this is the reflection for aluminum. It means it reflects most of the light. And it's white. For silver, it absorbs a lot of light, but however, it only absorbs in this low wavelength, this is the range of the visible light. It's beyond, it's absorbing this region, but it reflects most of the visible light. Then, therefore, we see it also white. However, gold is different. Gold, this yellow color, why it's yellow is different from others. And this is the spectrum of gold. You see it actually here. Gold absorbs many blue lights or all these purple lights and then reflects in this part. This is what we see by eyes. This yellow part dominated by the yellow color. And then why this gold is different from silver. Also from periodic table, you see silver is just above gold. It's much light. And then let's see. What determines this absorption of this part? Then the question is. And actually, what determines this reflection, just like this is the plasma on the surface, is like this depends. I may plot. we know about light is just like it absorbs light at some level and emission light during the hopping. And what actually usually happens is this s orbital to the d orbital. And good has like, let's see right here. It has 10 d electrons, and the s has only one s is halfly filled. There are 10. And if it absorbs light first in this way, then hopping and emission some light. And this emission actually tells you, give you the color, what you will see. Then it's not surprise if we have silver. If we have a second color as the gold, then what happened for gold? As we said, this sp contraction will just make the s energy a little lower. Actually, it's d orbital energy actually a little higher because d get expanded at the orbital, and this one get contracted. And then just this gap is much smaller. Then here, you see here, this energy is much smaller. And this is the relativistic effect already like generate a lot of impacts, like we already see by eyes, like from this liquid form of the mercury and to the yellow color of the gold. And it's not some tiny effect like milli or some milli effect in the atom. Actually, in many heavy elements, it can be really seen even by eyes. And there are also more examples. For example, like here, we talk about molybdenum and tungsten. Can you read the position of molybdenum and tungsten here? And they're in the middle here. They're both transition metals. And they're in which color are they? They're in 6, number 6. They're usually like, for MO, it's 4D5, 5S1. Tungsten is 5D4, 6S2. And this one is heavier. And then they have, in an atom, this is just in atomic level. And here you see here, because tungsten, the cis s orbital energy is a little lower, then there's one electron filling here. It's ground state, always preferring this way. And however, MO, the S is a little higher. And this is a consequence. Will cause the compound they formed will be very different. And for example, today we know there are many materials like MOS2 or MOT2, these materials. And but for tungsten, like tungsten S2, actually for tungsten material, because usually their crystal structure actually are different from the MO1. And this one usually is a distorted lattice, not the perfect, what you see, the structure, like a 2H or 1T structures. And usually the tungsten one are generally distorted. And yeah, also another really weird thing for gold is, again, there's a compound. It's formed by two metals, cesium, gold. Where's cesium? Cesium is here. Is this alkali metal, Cs. And gold is another metal. These two metals together, they will form a semiconductor. And how does it happen?